Hello, everyone. It is so lovely to see so many of you here today at SREcon. My name is Alexey Skorikov. I'm a technical program manager at Google, and I'm thrilled to be here today to talk about data monitoring in complex data pipelines. You will learn about one of approaches Google took in this direction, and we'll talk about lessons learned, how to make sense of full data dependency graph being a bedrock for data integrity solutions. Horizontal data monitoring at scale is one of them, and how you can practically instrument this approach in your organization. So let's get started. Speaking about the challenges, growing complexity of data pipelines and organizations poses more challenges to data reliability. More nodes and interactions in pipelines, more teams who build and maintain them, and higher organizational complexity. It's not an uncommon situation when a startup grows big to a large enterprise. And when it comes to rapid growth, this manifests in increase in technical debt, which contributes to this problem. It becomes harder to track end-to-end data dependencies and keep them well documented. Moreover, the documentation needs to be well maintained, and oftentimes this can be prioritized lower than delivering of some user-facing features. How can I figure out what data my system depends on and which systems are upstream? What are their service objectives and mitigation strategies? This question can be challenging at times in larger organizations. This poses additional threat and data integrity risk. As a result, teams see a decrease in operational readiness to deal with specific classes of outages and their impact on dependent data consumers. Increased risk of slow bleeds due to misconfiguration between producers and consumers, and at the same time, cost of incident resolution and revenue impact of outages may continuously grow. In complex data pipelines, risk of data corruption multiplies with each hop downstream. On this graph, you can see that when data gets corrupted in one of the data sets, this impacts all data sets downstream. The data arriving at points of consumption appears to be corrupted as well. And this poses a real problem. Without understanding of data dependencies, it would be tricky not only to mitigate an materialized risk, but also to plan for pipeline resilience. This is why it is vital to understand your data. Who writes and who reads it? Where are data dependencies? How business data flows through your pipelines, and what are the risks of outage and mitigation strategies at each particular hop through the pipelines? For any sizable organization, figuring out the data dependency graph manually is a non-starter. It would be even harder to manually keep it up to date. The question is, how can we find a way to map dependencies automatically based on access patterns? How can we convert pipeline spaghetti on the left to the need dependency graph on the right, ideally with minimum human intervention? For effective operational understanding, we need to be recording information about data access. Here are some ideas of how exactly the data can be harvested and provisioned. At Google, we record data access patterns at the level of job binary and process. We use several data sources for that, which are access log scrapers for storage systems, processing systems, and API endpoints. For monitoring purposes, it's useful to harvest metadata like modification time, writer, TTL, and logical size, for instance. Of course, for more sophisticated monitoring, you can think of gathering more metadata. To make sense of the recorded access metadata and events, datasets can be organized in a form of a dependency graph. And to add even more value to that, dimensions of interest can be grouped and linked to datasets and systems. For example, we use instance for network concerns, and grouping by data owner brings value for governance and privacy concerns. Environment stands for and helps to make judgment of a dataset criticality. Such graph helps to provide insights for distributed risks analysis, data flow and ownership traceability for mitigation and recovery planning, as well as holistic monitoring solutions. Basically, you could choose to add any kind of payload for to tie to elements of your dependency graph. For logical grouping, we use straightforward approach, datasets and systems. Now let's talk about instrumenting the solution. At Google, we use own ecosystem to record systems read-write activity. One can build a similar solution in their organization with the help of third-party or open-source software by combining different components. This can boil down to centralized log harvesting and distributed tracing at multiple levels. For example, microservices, data storage, and file systems. As output, one can use and one can get the graph itself and access metadata time series for monitoring purposes. So on this slide, I listed several open source solutions, but please keep in mind that these are only examples just to get the basic idea of how these might work out. It is important to keep the data annotated on a continuous level, as a continuous process. And regular Teams input is key here, but a lot of details can be inferred automatically as the system matures. One of examples of such automation would be inference of data ownership, and this can be based on a registry of data of systems in your organization with ties to teams who own and maintain them. So you can infer ownership of data by using the register of systems and their contact points. Data annotation enriches dependency graph with the understanding of criticality of datasets, data ownership, and mitigation strategies. So in this example, we also use data recovery objectives and data retention plans as points for annotation at the dataset level. Full curated data dependency graph is a bedrock for a whole plethora of data integrity solutions, which can be built on top of it to help address concerns we mentioned earlier. From slow bleeds detection to data validation and consistency checks, from understanding downstream risks to recovery plans, incident response. Further, we will focus on one of these solutions, horizontal monitoring for slow bleeds detection. Remember how risk multiplies with each hop downstream in a pipeline. Now that we have the curated data dependency graph, we can leverage it to build a blanket coverage monitoring to early detect slow bleeds. And slow bleeds can be a serious problem. Because of being unnoticed for weeks and months, they can potentially accumulate high business impact, financial or reputational. Common classes of slow bleeds are data staleness and data corruption. And multiple root causes can be there, from misconfiguration between data producer and consumer, bad migration, schema update, permissions issues, network issues, or resources starvation, concurrent writes, and changes in input data. As a result, producer system fails to update dataset on an expected pace or generates corrupted data, which leads to the consumer system downstream keeping to read the stale or corrupted data. As I said, this can go unnoticed for a durable period of time, and daily incremental impact is quite hard to detect as it depends on the particular business case. So for batch and streaming pipelines, there are subtle differences, but the problem is all the same. Good data in, producer not working as expected, and bad data out, bad or stale data. So freshness monitoring can be a successful approach by combining the curated data dependency graph with harvested update behavior over time. With this approach, one can deploy a comprehensive monitoring solution at scale for very little additional cost. It's worth mentioning that it won't catch all classes of slow bleeds, but it is valuable as a cost-effective additional layer of defense. So we successfully blended curated data dependency graph and harvested change patterns of change metadata of data sets, how they change over time, how their age, size, and other metadata change over time for our internal monitoring solution. And by applying analysis of change patterns, we provided several interfaces to detect slow bleeds, which are obviously alerting, historical insights in the form of age graphs and change patterns, and health reports to keep track of the whole picture. There are several types of anomalies which can be detected in this way. Such monitoring approach allows to detect some classes of these, and there are direct and inferred ways of detection. So for data staleness, the direct way of detection would be comparing age of a given data set with a fixed expected age threshold. The drawback of this approach is that you would need human interaction, human input to set the threshold. Indirect approach allows to detect an age threshold automatically based on change patterns analysis from the history of changes recorded. And this also helps to make sense of which data sets are static in order to exclude them from alerting and to increase signal to noise ratio. With the data corruption, things like logical size and writer metadata can be used. For direct inference, for direct detection, we can look at data consistency checks, like the number of items, their naming, their fixed size as expected. Whereas for inferred detection, we're looking for data explosion, like unexpected spikes and dips in logical size or rate of change in a data set, or malicious concurrency or unexpected writes change in data, the unexpected change patterns. So the key features of the monitoring are that, unlike direct access monitoring approaches, it doesn't require direct access to data. This reduces cost additionally, since teams don't have to provide permissions for the monitoring, and when it comes to scaling the solution for a large organization, this matters. The approach requires minimum configuration due to the leverage of the data dependency graph. So this reduces cost of adoption and usage, decreases risk of human error due to misconfiguration and monitoring of the monitoring, and provides a holistic health picture. One interesting feature here is that newly discovered data sets, as they crop in the dependency graph, they automatically get covered by the monitoring. I wanted to share with you one example of a monitoring solution based on this approach that we delivered internally in Google. So this is a feature breakdown for the features, which consists of 3 major layers. The first one is scoping. So we scope data, we scope the monitoring by using the age graph and looking at which data sets are critical, which data sets need alerting indeed. And this scales to multiple storage types: files, storages, and databases. In the detection layer, the horizontal monitoring does the major job by leveraging the gathered metadata for freshness monitoring and for age threshold auto detection. Same approach can be applied for corruption detection based on size and writer. For interface part, we provide graphs and comprehensive health reports. The monitoring can be flexibly configured by changing thresholds, but also can be switched to the automatic mode where no user intervention is needed to set the patterns. I'd like to share with you the lessons learned from the approach and the delivery of the monitoring that I described. One thing that monitoring definitely helped to detect real slow bleeds and real outages in pipelines, and that's really great that the approach worked out. But what's surprising, a surprising finding was that it also helped teams to detect potential technical debt in the data that was unused, the obsolete data. Such data poses data integrity risks as well, because it can bring miscommunication or confusion, where teams can start using incorrect data upfront. The monitoring approach also helped to raise awareness of upstream risks in data consumers. I must admit that signal-to-noise ratio was one of the challenges in this approach, and here are some steps that we took to improve the signal to noise ratio. First of all, we used understanding of which data sets are critical from the dependency graph to narrow down the scope of alerting, so that not to alert on non-critical data sets. Auto-tuning of age threshold is also a feature which allows to reduce toil and to increase accuracy of monitoring. Another thing that helped was recognition of multiple copies of the same data set across different charts or instances, and exclusion of obsolete and static data from alerting also helped here. And we did this by analyzing historical age data from the gathered findings. So we hope our findings were useful and can be applied outside Google. Understanding of the upstream and downstream dependencies can be challenging in complex data pipelines. And by harvesting data access patterns and building a data dependency graph automatically, an organization can open wide opportunities for data integrity solutions. And freshness monitoring is one of them. Thank you for your attention.